Hi everyone. So previously we had discussed on the tree algorithm, right? So today we will be discussing on the topic red black tree algorithm. Yeah. So red black tree algorithm. So let's get into the definition part here. So let's see what the definition part say here. A red black tree is a self-balancing binary search tree, right? It is a self-balancing binary search tree where each node contains extra bit for the color, right? So where each node in the tree, so whatever the tree it is, each node in the tree contains an extra bit for the color. Just remember this one. This point is very important. Yeah. So each node contains an extra bit for the color, either red or black. The name itself suggests, right? The color red, black tree. It ensures that the tree remain approximately balanced during the insertions and the deletions. What it does, it ensures that the tree remains approximately balanced during the insertions and deletions, keeping operations like search, insert, and delete in peak of logarithmic and time. Right? Search, insert, and delete in peak of logarithmic and time. Right? Let's go with the explanation part. So the first thing here, a red black tree maintains the following five properties. Just remember this is very important, right? So I have already typed this one. The code was lengthier actually, so I was practicing. I already typed the code actually, right? So I didn't wanted to type that much long code to the this one, right? For the video, right? So I'll just explain the code whatever I have written, not to worry. So first thing, let's go with the explanation part first thing. Yeah, here. A red black tree maintains the following five properties here. First property here is every node is either red or black. We know this one. Just keep this in mind. Every node is either red or black, right? So the root is always black. This one black. So the root will always be black, right? So every node will be either red or black, and it starts from the black. Actually, the root is always black. All leaves are black. All leaves NIL this one nodes are black. This is fine. If a node is red, then both its children are black, right? So no two reds in a row, right? No two reds in a row, right? If a node is red, then both its children are black. No two reds in a row. No two reds in a row. Right? So every path from a node to its descendant NIL nodes has the same number of black nodes called the black height. Again, every path from a node to its descendant NIL nodes has the same number of black nodes called the black height. Right? So these properties, what it guarantees, these properties guarantee that the longest path is at most twice as long as the shortest one, keeping the tree balanced, right? So first we have assigned the red to the this one red itself within the string. Same goes with the black as well. So let me explain you this one step by step, right? The algorithm part. So first we are defining the colors as constants here, red to red as well as the black to black, as I've said. Next we are going with a this one node class. What does it do here? We are defining the structure of node here, right? So don't get confused. So this one data, we have initialized data, nothing but we are storing the node's value, right, within the data, right, as data. Sorry. So next we are initializing the color to red, meaning every new node starts as red here, right? So this is nothing but the left child, this is nothing but the right child, and this is nothing but the parent preference, right? So next we are going with a red black tree here. So this class, so we are defining the red black tree, right? So we are defining the red black tree, nothing but the red black tree class, right? So here within the initialization part, so this one nil dot this one we have set this one to the node of 0, right? So this one line number 39, actually, this is the sentinel NIL node, which acts as leaf, and this one, a self.nil, whatever I have initialized the root to, initially root points to nil, right? So initially root points to nil. Yeah. So next, let's go with the left rotate around the node X. So next we went with the left rotate around node X, right? So this is fine. Next, after this, this is nothing but the right rotate around node Y, right rotate around the node Y. Next, we are going with this one, fix insert. So what does the fix insert method do? Let me explain you this one step by step. So this fixes the tree of the insertion to maintain the properties. right? So let's see what are the things that we are doing, right? So within the fix insert. So here, this is nothing but the uncle, right? So uncle, right? So this is nothing but within the uncle. So we are going with the first if condition. The first if condition is nothing but the case one here. So when uncle is red actually, right? When uncle is red actually. Next, we are going with the second case, nothing but when node is the right child. When node is the right child, right? So when node is right child, right? So just remember this one. Yep. So just remember this one. Sorry, when node is the right child, this one, not this one. This one when node is the left child. The same thing. This one when node is right child, right? So let's go with the third case here when node is left child, right? So this one I have already mentioned here when node is left child, right? So this is fine, I believe. Next, let's move on with the next one. So we have to insert a node into the tree as well. Quite obviously, we have to insert a node into the tree. For that, we have written one more function named insert here. We have written one more function named insert here. So this is fine. So as discussed in the explanation part, so I said that we'll be going with the in order traversal for checking the balance and color, right? So here we have went with the in order method, right? So in order method, nothing but we are going with the in order traversal for checking the balance and the order, right? So finally, this is nothing but the demo usage or the example usage, right? So this is the thing, but uh, so we are going with the elements 10, 20, 30, 15, and 25. So then finally we are going with a print statement just for the this one interactive purpose. So what is the output that we need to get here? So output that we need to get here is in order traversal value of color. First one 10 black. The root always has to start with a black actually, right? So 10, first one we have to get this one black, and 15 every node starts with a new node starts with a red, so 15 has to be red, and 20 again it has to be black, and 25 we have to get a red here, and 30 we need to get black. So why we have to get in this order? So let me explain you. 10 black because it is the smallest element. So in the example that we have considered, so this is the smallest element in the array, right? So 10, 20, 30, 15, 25. 10 is the smallest element, and it is set black because it's set black as per the red black properties, right? So first root it has to start with a black, right? So then 15, 15 it is red because it is newly inserted node, and a newly inserted node always starts with a red, right? So balanced after, this will be balanced after rotations, not to worry, right? So 20 we have set this one to the black, or we will be getting the output black because this is the root node again, the new one, right? So new node, and the root has to always start with a black actually, right? Root node always black, right? And the fourth one is 25. 25 is the right child of the root. 25 is the right child of the root. So this is kept red to maintain the black height, right? So this is kept red to maintain the black height. Finally, we are going with the 30. 30, it will be black because it is far right leaf, and it will be set to the black for balancing the consistency, right? So one more thing here, just note this down. The colors alternate properly here, right? The colors alternate properly, and the black height remains the same across all paths. The black height remains the same across all the paths, showing the red black tree is correctly balanced, right? Red black tree is currently correctly balanced, right? So this is the output actually that we need to get. So now we have the idea of the algorithm, and we have discussed the output part as well. Let me run the code now. Yeah. So I'll just give control J here, Python followed by the file name dot pyc in order traverse a value color 10 black, 15 red, 20 black, 25 red, and 30 black, right? So we are getting the desired output, right? So the whatever the code that we have written works absolutely correct, right? So we are getting the desired output. Now, as this is it for the algo, right? So we are done with the algorithm. So let me do one thing before hopping into the next algorithm. Let me explain whatever, or let me summarize whatever we have learned so far, right? So what is the purpose of this? What is the purpose of this algorithm? So red black tree, what is the purpose? Simply we cannot write some algorithm, right? So there should be some purpose for it, right? So basically what's the purpose here? Meaning, uh, in the sense, so will be keeping the binary search tree balanced for guaranteed big of logarithmic n purpose, right? This one, big of logarithmic n performance, right? So next, what's the key idea? What's the key idea here? What's the idea basically? Yeah. So we will adjust the node colors. Initially, I have said you, we will adjust the node colors here and rotate the tree when inserting, right? And rotate the tree when inserting or deleting, right? Insertion or the deletion. Yep. So this is fine, I believe. So the main key idea here is we'll adjust the node colors and rotate the tree when inserting or deleting. Now the third part is operations, right? So when I say operations, so insert, delete, and search all run in big of logarithmic n time. Insertion, deletion, as well as this one search all run on because of logarithmic n time, right? So because of logarithmic n time. So this is fine. The final one is fourth one. So here real world use, right? Use cases. Use cases. It is commonly used in the this one. C++ libraries, whether it may be this one CPP STL map. Actually, it is used in the CPP STL map, right? So this is one of the thing, and we will be making use of this in the Java tree map as well. Java tree map as well, and we will be making use of the red black tree mainly in the Linux kernel data structures. Remember this, we will be making use of it within the Linux kernel data structures, right? So I'll just write here Linux kernel data structure. So this is one of the edge case, sorry, not the edge case, sorry, this is one of the use case, right? So real world use cases are, it is commonly used in the libraries like C++ STL map, Java tree map, and Linux kernel data structures, right? So these are some of the points that I wanted to discuss with you guys. You have to know this one at any cost when it comes to the red black tree algorithm. So you need to remember these things at any cost, right? So this is fine. Let me delete this one. So we are done with the red black tree algorithm. So next, we will be discussing the AVL tree algorithm tomorrow. So for now, this is it. Thanks for watching, guys.